Hello everyone! Have you ever stumbled across datasets with missing entries? Have you ever filled these entries with the mean of the column and hoped for the best in vain? Well, a denoising autoencoder with mask attention, or DAEMA, may be the solution. It leverages an attention mechanism specifically designed to handle missing data. Thanks to that, DAEMA obtains state-of-the-art results for data reconstruction in terms of reconstruction error and downstream task performance. I am Simon Tillon, and I am going to present you this solution developed at Euronova by Mohamed Oussama Javaid and me, with the help of Damien Fourrure, Nicolas Pozocco, and Thomas Peel. The first question to be asked is, what is the problem? Well, nowadays, many datasets have missing entries. Removing the samples with missing entries or filling these with the mean is not always a good solution. In the best case, the problem will be a lack of data, which is easy to spot. In the worst case, a bias will be induced in the dataset and learned by the algorithms. Missing data imputation consists in filling a dataset with missing entries so that it can be used for other purposes, such as a downstream machine learning task. To perform this task, three types of missingness have been defined. Imagine you are a doctor and you can take the temperature of your patients. However, you don't want to take the temperature of all of them. The temperatures you won't take will therefore be missing data. Depending on how you choose whose temperature to take, the missing data can follow three types. If you take your decision randomly before even seeing the patients, the missingness will be referred to as missing completely at random, or MCAR. The fact that a value is missing has nothing to do with the data. If you choose to always take the temperature of the old people and choose randomly for the others, the missingness will be referred to as missing at random, or MAR. The fact that a value is missing depends only on known data, here the age. If you choose to always take the temperature of the people for whom it seems useful, for example, those who seem to have a high temperature, and choose randomly for the others, the missingness will be referred to as missing not at random, or MNAR. The fact that a value is missing depends on the missing value itself. This categorization is used in the literature for different aspects that are out of the scope of this video, including an analysis of the bias introduced in the dataset and the methods suitable to deal with it. Paradoxically, the more professional you are as a doctor, the more difficult it will be to manage the missingness. Draw your conclusions. Formally, the task considered here is the following. We are given samples X with missing values. We are also given the corresponding masks M, that is, vectors indicating which values of X are missing. Our goal is to learn an imputation function f, which takes x and m as input and produces plausible values for the missing values of x. The performance of such a function is measured using different metrics that will be introduced later. To learn this function, we propose DAEMA, a denoising autoencoder using a new mechanism we called mask attention. Here is the intuition. First of all, we start from a simple denoising autoencoder. A neural network encodes the data into a latent space, and this latent space is decoded by another network to reconstruct X. These networks are the feature encoder and the feature decoder. For the network to learn to impute missing data rather than implement the identity, an artificial missingness is added to the data before feeding it to the network. Then, we ask the question, what if, instead of using a single feature encoder taking all input features into account, we used an ensemble of feature encoders, each specialized on a subset of features. For example, the first feature encoder would learn to compute the latent representation based mostly on the first and the third features, while the second one would do the same based on the second and the fourth features. For the example on the slide, the first feature encoder will perform very poorly as both its important features are missing, while the second feature encoder will perform almost as if the data was complete. In this case, we would like to give more weight to the second feature encoder as it will perform better. The question becomes how to weigh each latent representation. This weight will obviously depend on the encoder performance, which, in turn, depends on the missingness pattern of the imputed sample. A way to go is therefore to learn a feature selector fs, which takes the missingness pattern, or mask, as inputs and produces a set of weights for the different encoders. A virtuous circle appears as a result. At initialization, an encoder may receive slightly more weight for a few missingness patterns than for others. Because of that, the samples following these patterns have more weight on the optimization of this encoder. As a result, the encoder specializes in these patterns, and therefore obtains better performance for these. Finally, as it obtains better performance for these patterns, the feature selector will learn to give it more weight for these patterns, and the loop is complete. But let's not go round in circles. Here is the final architecture of DAEMA. If we replace the whole attention mechanism block by a single feature encoder, we obtain the denoising autoencoder introduced earlier. In the attention mechanism block, there is a feature encoder producing many latent representations. Empirically, this is better than having multiple feature encoders, each producing one latent representation. At the bottom, there is the feature selector, taking a mask as input and producing a set of weights for each latent feature. These are used to make an average through softmax, product, and sum operations in order to obtain the final latent representation of any sample. As shown in the previous slide, this architecture produces a virtuous circle such that each intermediary latent representation is specialized in some specific patterns, leading to a missingness-robust final representation. This representation is then used to impute the original sample. This architecture is very promising as it obtains state-of-the-art performance. The baselines used to compare to are DAE, the denoising autoencoder at the core of DAEMA, AIMNet, a state-of-the-art neural network which uses attention in a different way than DAEMA, MIDA, another denoising autoencoder, and MISForest, a state-of-the-art algorithm using random forests. The latter is not directly comparable as it is meant to impute a whole dataset at once rather than to learn an imputation function. The mean imputation and perfect reconstruction are shown as indicative lower and upper bounds. The results are computed on 7 publicly available datasets processed to have missing values following a missing completely at random setting. The results are the reconstruction error measured as the normalized root mean square error on the missing values, and the downstream task performance obtained by random forest after the dataset was imputed. DAEMA is on par with MISForest and better than the other baselines on most of the datasets. Specifically, even though AIMNet generally obtains better results than the basic autoencoder, adding the mask attention to the autoencoder is enough to reverse the trend. The same experimentation was run using a missing not at random setting, with similar results. We also analyzed the robustness to the missingness proportion on 3 of the 7 datasets. As can be seen on the graphs, where lower is better, Miss Forest and DAEMA obtain similar results, with a slight advantage to DAEMA for high missingness proportions. Strangely enough, for high missingness proportions on the glass dataset, the Miss Forest and DAEMA algorithms are significantly worse than the mean imputation, which is highly unexpected. Our best guess is that it is due to outliers in the glass dataset. DAEMA being validated, there is still one important point to be made. The mask attention of DAEMA is not only about data imputation. Indeed, it can be added to almost any neural network to make it more robust to missing data. Let me explain that. Imagine you have a task and a neural network to solve the task. To make use of the mask attention, the network has to be split into two parts, a feature encoder and a downstream network. Then, the feature encoder has to be adapted so as to produce multiple latent representations instead of one. Finally, the mask attention can be used to average these representations into a final, missingness robust latent representation. This being said, all important points have been discussed. As the conference has only just begun and there are many more interesting presentations to come, I will consider this video a success if you remember at least the following points. First, the mask attention is not about missing data imputation alone, but can be used as an addition to most neural networks. Using it will make the network more robust to missingness. Yet, DAEMA can be used directly as a highly competitive imputation algorithm. Thanks to the reviewers, to the conference, and to those of you who will make use of our work. If you have any questions, we will be glad to answer these by mail or during the Q&A session.